Let's go. Oh, well, hello there. Today, we're going to talk about instantaneous rate of change versus average rate of change. This is the essence of introductory calculus. Understand this, and you are good to go. All right, let's take a look at this problem here. We're going to drop a rock off of a 100-meter tall building. Equation, 100 minus 4.9 t squared. All of you should recognize the 4.9 as half of 9.8 meters per second squared. Yes, the gravity constant in the metric system. But that's beside the point. Let's think about what this graph looks like. Well, as you know from Algebra 2, this is an opening down parabola with a vertex at 0, 100. And sure enough, here goes the rock. Good. All right. Now, what's that x-intercept? Well, it's the value of t that makes h 0. So 100 divided by 5 is 20, square root 4-ish, right? So this is, the square root of 100 divided by 4.9. Okay, that's that x-intercept. So we're interested, though, first of all, in the average rate of change between 0 and 3. Well, what's that saying? Well, that's like saying if you travel 100 miles from time 0 to time 5, right? What's your average rate of change? Well, that's 20 miles per hour, of course. Does that mean you went 20 miles per hour the whole way? No, that's the average rate of change. So let's find the average rate of change here from 0 to 3. Let's see, how would we represent that graphically? Well, let's make a smaller graph here. Here's my rock. Now, you can think of this as water, and the rock goes through the water. What's that average rate of change? That average rate of change is the slope of that secant line. Now, can you see how that secant line goes beneath the graph? Let's make sure you can clearly see that. And I'm just going to estimate here the intersections, okay? But can all of you see that this graph, that this green line touches the graph in 2 spots? And basically, I find the slope of that line. That gives me the average rate of change. Oh, how do I find the same way you've always done it in your whole life? We'll say h of 3 minus h of 0 over 3 minus 0. Does that look familiar to you? That's the slope equation for middle school. All right, so here we go, and we'll just plug those right into our calculator. So I'm not going to do anything fancy here, just plug them right in. So let's do that, okay? So let's do 100 minus 4.9 times 9 minus 100. Because 4.9 times 0, right? So let's see if I've got the parentheses right there. We'll divide that by 3. We should get an average rate of change of negative 14.7 meters. In this case, it'll be meters per second. So let's write that down. Negative 14.7 meters per second. That makes sense. It should be a velocity. It's a rate of change. And let's just say here, remember, this is meters in seconds to make your physics teacher happy. We'll put our units on there. Okay, negative 14.7 meters per second. No problem. That's the average rate of change. Now, this is why you take calculus. We want to find the instantaneous rate of change. Well, what am I talking about here? Again, let's take a look at our picture. I'm going to exaggerate the picture here a little bit. What am I looking for here? I'm looking for the tangent line at 2. Okay? So remember, this was the slope at 0 to 3. This is the tangent at 2. So instantaneous rate of change is another way of saying slope of the tangent line, which is another way of saying derivative at 2. I've given away the secret. Instantaneous rate of change, slope of tangent line, derivative of function. Now you know what all the calculus teachers know. Okay, that's it. I just gave you the secret. So I'm looking for the derivative of h when t equals 2. That is the words. You drop that phrase at your next cocktail party, and people are going to love you. You'll be the most popular person there. Either that or everybody will run away from you. But the people who don't run away, marry them. Okay, now let's continue on. I want the derivative of h at t equals 2. Oh, what's the formula for derivative? You learned it yesterday. The limit as h approaches 0 of, in this case, we'll say f. Now remember, this h is different from that h. Sorry about that. This is, just, you understand what I'm talking about. F of 2 plus h minus f of 2 all over h, okay? You know what, let's, derivative of y when t equals 0. I don't like using the letter h here. I don't want that to confuse you. So let's say y is the height, okay? Okay, let's just be clear there, all right? I don't want there to be any confusion with our variables. All right, so let's set up where we are again. Sorry, let's review. We start dropping a rock off of the 100-meter building. There's the graph, algebra 2, no problem. We want to find the average rate of change from 0 to 3. Oh, okay, slope, right? How did we do that? We did, this point here is 0, 100. This point here is 3, 100 minus 4.9 times 9, right? We plug those into here, and we get negative 14.7. Then we want to know the instantaneous rate of change, which is the same thing as the slope of the tangent line, which is the same thing as the derivative. Well, let's do it, man. Put on your algebra pants, and let's figure this out, okay? So let's go right over here. And remember now, we're going to do f of 2 plus h minus f of 2 over h, the limit as h approaches 0, okay? Yeah, okay, there it is right there. 100 minus 4.9 times 2 plus h squared minus 100 minus 4.9 times 2 squared, all over h. Okay? And now we just grind this out. There's no secret here or anything. We're just going to grind this out. But something pretty cool is going to happen in the end. Things are going to cancel away, and this is going to simplify nicely. So let's go ahead and do it. Okay, so I'm just going to try to simplify this numerator a little bit. 100 minus 4.9 times 4 plus 4h plus h squared minus 100 plus 4.9 times 4. And we're going to put all of that over h. Now, can we do this? Totally. We can totally do this, right? We can totally do this. Here we go. We're going to say, well, I can simplify this a little bit, can't I? There's 100 minus 100. throw that away, right? Now, let's try to work this out. Negative 4.9 times 4. Negative 19.6. Negative 4.9 times 4h minus 19.6h. Negative 4.9 times h squared minus 4.9h squared. How about negative 100 plus 4.9 times 4? Negative 80.4 minus 80.4 all over h. Now, here's what happens, right? Oh, whoops, that 100 wasn't there, was it? So this is just plus 19.6. Remember, because we subtracted those hundreds off at the beginning of the problem. Now look what happens. The 19.6's go away, and I'm left with negative 19.6h plus 4.9h squared all over h. Well, now I can factor out the h and simplify this to be negative 19.6 plus 4.9h. As h goes to 0, that's going to be negative 19.6. So what does that mean? That means that once I simplify all of this, this becomes negative 19.6 meters per second. And that is the slope of that tangent line. And furthermore, that is exactly how fast that rock is falling when t equals 2. Okay? Now, you can rewind the video and pause it and stare at that algebra until it makes sense to you. But the idea here, you can do this. I want you to understand what's happening. The rock is falling. Pretend this is the rock. We're going to stop it, boom, right here. How fast it's going at that instant? Negative 19.6 meters per second. Piece of cake. And that, my friends, is your derivative.